Welcome to today's paper reading. Today's paper is titled, RPBG, Towards Robust Neural Point-Based Graphics in the Wild. This paper was published on AR14 by Qingtian Zhu and colleagues from the University of Tokyo and XREL. The abstract highlights the growing interest in point-based representations for novel view synthesis due to their intuitive geometric representation, simple manipulation, and faster convergence. However, these methods face challenges such as noisy, patchy points and unbounded scenes, which are common in real-world applications. To address these issues, the authors propose robust point-based graphics, RPBG, which enhances the neural renderer to correct point visibility and in paint incomplete rasterization. This approach aims to make the rendering process more robust to varying datasets and outperforms existing methods, including state-of-the-art and RF-based variants. Novel view synthesis, NVS, is a fundamental task in computer vision and computer graphics, aiming to synthesize new views from a series of posed images. This has been a subject of research for decades. Among the solutions, NERF and its variants approximate an implicit scene representation using a neural network that maps 3D coordinates and view directions to colors and densities. RPBG, on the other hand, focuses on a robust point-based re-rendering approach, enhancing the neural renderer and improving robustness and generalizability over traditional methods. Figure 1 illustrates the robustness and scalability of RPBG in achieving high-quality re-renderings across various datasets. On the left, the graph shows RPBG's superior performance in terms of PSNR compared to the baseline and state-of-the-art RF-based methods. On the right, the figure displays point clouds with visualized camera trajectories and the corresponding re-rendered novel views, showcasing RPBG's ability to handle diverse scenes effectively. This demonstrates RPBG's great robustness and scalability, making it a strong candidate for real-world applications. In the context of neural view synthesis, radiance fields, RF, are characterized by assigning each position with an anisotropic color and a density. This allows for the use of differentiable volume rendering, which is facilitated by a multilayer perceptron, MLP, that maps coordinates and view directions to radiance values. Various parameterization strategies have been developed to enhance the rendering quality for different types of scenes, such as forward-facing, 360 degrees unbounded, and large-scale scenes. However, these case-by-case strategies limit the generalizability of the methods. On the other hand, point-based graphics utilize point clouds as a flexible and sparse representation of 3D geometry. These points are often replaced with surfells and blended using splatting techniques. Neural rendering, which learns to render high-quality images in a data-driven manner, has been applied to enhance point-based rendering, particularly in the context of autonomous driving and large-scale training. The primary challenges in neural point-based graphics, NPBG, revolve around patchy triangulation, wrong point visibility, and a lack of context for re-rendering. Patchy triangulation is problematic due to non-Lambertian surfaces and textureless regions, leading to poor quality points. Wrong point visibility arises from the inherent sparsity of points and can be exacerbated by erroneous depth thresholds. The lack of context in re-rendering incomplete point clouds limits the effectiveness of the neural renderer, particularly at high resolutions. These issues collectively hinder the robustness and accuracy of NPBG in handling complex scenes. Figure 2 illustrates two challenging scenes from the TNT dataset for the neural point-based graphics, NPBG, method. The top scene is an auditorium, characterized by extremely sparse walls and ceilings, which poses difficulties for accurate rendering. The bottom scene is a museum, where the sparsity of points complicates the handling of occlusion and visibility. These examples demonstrate the limitations of NPBG in rendering complex scenes with sparse and patchy point clouds. The robust point-based graphics, RPBG, is introduced as an enhanced version of NPBG, focusing on robustness in generic scenes. The modifications made to the pipeline and training paradigm are designed to improve performance under challenging conditions. Key modifications include the implementation of a downgrade-aware neural renderer, enhancements to point triangulation, and adjustments in environment modeling. These changes aim to leverage neural networks to yield visual details more effectively. Figure 3 illustrates the overall pipeline of RPBG, which is an enhanced version of NPBG focusing on robustness under generic scenes. The process begins with point triangulation, where a 3D proxy is triangulated for re-rendering using posed images, initializing its geometry-bounded neural texture. Next, in point rasterization, the points are rasterized to the given camera in a non-differentiable manner, indexing the texture with the fragment to obtain the neural buffer. A learnable point-size neural texture 10 is also optimized during this step. The core of the pipeline is neural rendering, where CNN performs the restoration from downgraded neural buffer to photorealistic images. The network and neural texture are optimized end-to-end by image-level losses. Additionally, an offline point cloud augmentation strategy is introduced to address the issue of patchy triangulation under challenging conditions. Figure 4 illustrates the architecture of the downgrade-aware neural renderer in RPBG, focusing on the adaptive handling of severely erroneous point visibility. The key component, the downgrade-aware convolution (DAC) module, is highlighted for its ability to manage complicated point visibility with patchy triangulation. The visualized attention map demonstrates how DAC effectively adapts to these challenges, ensuring the neural renderer can decode high-quality visual information from patchy buffers. The experiments cover a diverse range of datasets to test the generalizability and robustness of NVS methods. Key datasets include the free dataset with 7 free trajectory scans, tanks and temples with 9 scans, and MIL-19 with 2 large-scale aerial scans. Additionally, challenging datasets such as ScanNet++, OMMO, and ETHMS are included for thorough evaluation. The evaluation metrics used are PSNR, SSIM, and LPIPS, VGG, which are crucial for assessing the quality of synthesized images. Figure 5 presents a visual comparison of neural view synthesis, NVS, methods across various scenes. The scenes include the sky and hydrant from the free dataset, courtroom and train from the tanks and temples, TNT, dataset, and Dia Temple and Memorial Hall from the GigaMVS dataset. The methods compared are RPBG, hours, Gaussian splatting, NPBG, and F2 NERF. RPBG demonstrates superior performance in structural similarity index, SSIM, and learn perceptual image patch similarity, LPIPS metrics, which are crucial for capturing high-frequency image details. The visual results show RPBG's ability to produce more harmonious and visually consistent renderings, especially in comparison to Gaussian splatting and F2 NERF. This figure highlights RPBG's robustness and effectiveness across different datasets and scene types. Figure 6 illustrates the impact of using a default feature vector for environment modeling in an unbounded scene. The figure compares 2 scenarios, A, without environment modeling, and B, with environment modeling. This study highlights how leveraging a default feature vector can influence the rendering quality and robustness of neural point-based graphics in the wild. The results show that incorporating environment modeling significantly reduces artifacts and improves the overall visual fidelity of the rendered scenes. Figure 7 presents a challenging case within the train scene, focusing on a zoomed-in view that highlights complex occlusion and thin objects such as handrails. This detailed perspective underscores the difficulties in rendering such intricate details, emphasizing the need for advanced techniques to handle these scenarios effectively. Figure 8 illustrates the re-rendering quality measured by PSNR across different point qualities on the church dataset. The RPBG method demonstrates its robustness by maintaining a 14% drop in PSNR, which is notably lower compared to the 25% drop observed in NPBG and the 14% drop in NPBG++. This indicates that RPBG effectively handles varying levels of point sparsity, ensuring consistent and high-quality re-rendering results. Table 1 presents a quantitative evaluation of various state-of-the-art neurovolumetric scene (NVS) methods, including NERF, TensoRF, NERF++, F2 NERF, MegaNRF, NPBG, NPBG++, Gaussian splatting, and our method, across different scene categories such as free trajectory/unbounded, inside-out, large-scale, and sparse view scenes. The evaluation metrics used are PSNR, SSIM, and PIPs, which are compared to assess the performance of each method. The table also indicates the number of scenes in each dataset used for the evaluation. Table 2 presents an ablation study on network designs using the TNT dataset. The key metrics reported include inference time and memory consumption, both of which are measured at a target resolution of 1920 by 1080. This table is crucial for understanding the performance trade-offs associated with different network design choices, providing insights into how various configurations impact computational efficiency and resource usage. Table 3 presents an ablation study on environment modeling for two unbounded scenes, Caterpillar from the TNT dataset and Sky from the free dataset. The table highlights the equivalent overheads in terms of hashtag points, times 106, when applying various strategies. This analysis provides insights into the performance and resource consumption of different environment modeling techniques, which is crucial for optimizing the rendering process in unbounded scenes. The effectiveness of RPBG is primarily attributed to its use of triangulated 3D points, which simplifies the search complexity compared to RF-based methods. Additionally, the patch-wise rendering scheme enhances perceptual quality. However, RPBG faces limitations such as high storage requirements for CNN parameters and neural textures, which grow linearly with the point cloud scale. The non-local neural renderer also hinders editability. Temporal consistency issues arise from patchy triangulation, relying on in-painting, and the flicker issue, which has been discussed in related literature. In this paper, the authors introduce RPBG as a robust and practical alternative to NPBG, a baseline method in point-based neural view synthesis. RPBG performs neural re-rendering on triangulated points and is designed to generalize to a wide range of scenes beyond well-captured scans. The pipeline of RPBG is reformed based on insights from RF-based methods and low-level image restoration techniques, addressing key issues in NPBG. Extensive experiments on diverse datasets demonstrate that RPBG achieves consistently superior results compared to state-of-the-art RF-based and point-based NVS methods, particularly in metrics that emphasize human visual perception. This indicates the robustness and generalizability of RPBG without the need for case-by-case parameterization across different scenes. Thank you for watching.